here. So I'll be talking about generalization beyond data. Distribution is all you need, question mark. So we'll try to find an answer to this question through the talk. Right. So if we look at the literature of statistics, there has been for a long time an obsession with the mean. So for example, here's a quote from Galton, who was regarded as one of the originators of regression, that it's difficult to understand why statisticians commonly limit their inquiries to averages and do not revel in more comprehensive views. And here's another quote from this article from Friedman et al. That one of the famous top 10 reasons to become a statistician is that statisticians are mean lovers. And it's of course a bit jokey, but it's also kind of true. But in recent years, there has been a trend to go beyond the mean. So, for example, it has been made explicitly in this paper from about 10 years ago that the ultimate goal of regression analysis is to obtain information about the conditional distribution of the response given a set of explanatory variables. So they kind of, for the first, or maybe not the first time, but they made it explicit that the conditional distribution, the full distribution, is the goal. And if you look at the machine learning area, they have been actually pursuing the same goal from a different perspective of sampling or data generation. And so if we ask what's the most popular area these days in machine learning, it must be generative AI. So just try to move this a bit. Yeah. And I suppose we've all been using this, one of these popular AI tools like ChatGPT, Cloud, DALL-E for text generation, image generation, or video generation. And so these are just the pictures, examples of pictures generated by DALL-E 3, which are very kind of realistic and as if they were produced by some human artists. And so this looks a bit, might seem a bit far from classical statistics, but we can, of course, argue about what we mean by classical statistics, but it seemed to be a bit far. And so in this talk, we're going to try to discuss how generative AI can be actually useful for one of the statistical problems and one of the challenging ones, which is the generalization problem. So far it's been vague what we mean by generalization, but through the next few slides, I'm going to try to concretize a bit and formalize a bit with the particular problem that we're going to talk about. So if we look at the classical regression setting, we have a set of predictors X and response Y, and we often collect training data from a certain distribution, a joint distribution over X and Y. And the target is often the conditional distribution of Y given X under a test for a test data, or it can be its functionals like the conditional mean or conditional quantiles. And so the classical setting, in a classical setting, we would assume the test distribution is the same as the training distribution. And that's the case for both the distribution of the covariate and the conditional distribution of Y given X. So, and then the classical method is to fit the target directly on training data by empirical risk minimization. And so that's the classical story. But we could meet some potential problems, especially for the cases where an ERM fit and empirical risk minimization fit on training data may not be optimal. And that's the case for example, if we have the following cases. So the first case is the so-called out of support covariate shifts. So it's a special case of covariate shifts where we go completely beyond the range that we observed. And so that's also called known as extrapolation. So, and the second scenario is more about conditional shifts. So if the distribution of Y given X is no longer the same for the test and the full training. And the third example is actually causal inference. So because we often just collect data of, let's say, treatment, outcome, and maybe some covariates, but that's the observed distribution. We can only get to observe the joint distribution of all of them. But the target in causal inference is often the causal effect, which is like the interventional distribution of the outcome given a certain treatment. maybe in the presence of latent confounder. And in that case, the target is not directly observed. It's not something we can directly get from the observed distribution. So for all of these cases, a simple empirical risk minimization on the training data wouldn't be optimal. And so the common thing about all of these problems is that we need to generalize beyond the observed data distribution. Okay. And so in this talk, so there are many like existing excellent frameworks to do this generalization problem. But in this talk, we're going to look at a distributional perspective. And so what we mean by that, we're going to say in this slide. So we're given just any inferential target, let's say the conditional mean function under distribution shift or the treatment effects. So whatever inferential target we start from, we always kind of suggest people to try to estimate the full distribution of your training data. And we're going to try to argue that's going to be helpful for better generalization beyond the observed distribution. And the intuition here is that you're given a training data, you're given an observed data, and you want to make full use of it, right? And in a statistical sense, the kind of maximum amount of information you can get from the data is the full distribution. That's all you can get from a statistical sense. So we just suggest people to just estimate the full distribution and then see what you can gain from that. So through the talk, we're going to demonstrate how you can actually gain for this particular generalization problem. So again, in the remaining of the talk, we're going to talk about all of these three cases: out of support, covariate shifts or extrapolation, conditional shifts, and causal effect estimation. So far, we've been basically already touched upon the two main themes of this talk, and I'm going to just repeat them at this point to just hope that you will keep them in mind throughout the talk. So the first theme is more like a statistical one. It's more specific. So it's just what we just talked about in the last slide. Estimating the full distribution is going to help us yield better generalization. And the second theme is broader, it's a bit broader. So it's more from an algorithmic perspective to say generative AI as a tool can bring actually new potential to statistics. And we hope throughout this talk, you're going to be slightly more convinced about these two themes. Okay, so the specific outline of the remaining of the talk is going to be like, we need a method. We suggest people to estimate the distribution. So we need a way to do that. So we're going to first introduce a simple but flexible generative model method to estimate distribution. So the method is called ingression. And then we're going to talk about a few adaptations of ingression to the three generalization problems that we mentioned earlier. Okay? Right. So here we're going to start from this this framework that is trying to learn the distribution via generative model method. So again, the target is the conditional distribution of y given x. And now we try to build a generative model to describe this target distribution instead of using density, a conditional density or conditional CDF and so on. So now we look at the generative modeling approach. So that's to say, we write the response variable y as function g of predictor x and some additional noise variable epsilon. So that's how we build the model. And here epsilon comes from a predefined distribution like a standard Gaussian. And this map G, the transformation G, is a mapping from the predictor noise pair to the response Y. And that's often parameterized by neural networks. So under this modeling framework, the goal of estimating the distribution then becomes to find a map G such that the distribution of G of x comma epsilon for a fixed value of x and randomness comes from epsilon would follow this target conditional distribution of y given x. And once this goal is achieved, we essentially have a model that allows us to sample from this target distribution. And then we can basically estimate everything based on sampling. So that's a brief, like a rough idea of this whole framework. And we're going to look at more concrete examples in two slides. Okay. So now we try to learn generative model, we try to learn the distribution, we need a way to assess how well the distributions are to compare different distributions, right? And the way we are using here is the so-called proper scoring rule, and we use one particular proper scoring rule, which is called the energy score. And here's the definition. So given a candidate distribution P and an observation Z, which is a single value for now, the energy score is defined as the following. So there are two terms in this score. We first look at the second term. So the higher the score, the better it is. So the second term is the expected distance from any random draw from this candidate distribution and this single observation. So we hope this term to be small. So like basically all the draws from your distributions will be fairly close to that observation Z. And in addition, we also have the first term, which penalizes the expected distance between two independent draws from your candidate distribution. And we hope that term to be not too small so as to avoid the degenerated case of a point mass. And this energy score is a strictly proper scoring rule, which means that for any distribution P, this expected energy score, when we take expectation over this observation Z coming from a certain true observation distribution P star, so this expected energy score is maximized if and only if this candidate distribution is the same as the true observation distribution. And so this property kind of suggests us that we can use this energy score to design a loss function. And this is exactly what we're doing in ingression. So this is our simple distributional learning method. We call it ingression. So En comes from energy score. So we define at the population level, we define the ingression solution as a minimizer of this expected negative energy score. So our candidate distribution is now the conditional distribution induced by the generative model. So it's basically the distribution of this random variable. And the good thing about energy score is that it's very easy to compute. So we can equivalently write the loss function, the objective function, as the second row. So in a second row, if we look at it, it's not that, it's kind of very similar to a standard regression loss. So if you think about this generative model as your regression prediction model, then the first term is trying to make sure it's trying to minimize the distance between your true observations of your response and your predictions from your model. And so in a univariate case, because we don't take the square here, so in a univariate case, this is exactly mean absolute error minimization. But just in addition, we also try to penalize we try to encourage the model to have sufficient variance. So we hope the model doesn't ignore epsilon. So for different independent draws of epsilon from a predefined distribution like standard Gaussian here, the model would be sufficiently different. So that's what the second term is trying to do. And intuitively, because that's intuition, what these two terms are doing. And what we can show, because the energy score is a strictly proper scoring rule, so we have this proposition which says that when the model is correctly specified, which is hopefully a very mild assumption when we parameterize the model G by neural networks, we can show this as solution ingression solution G tilde of x comma epsilon follows the target conditional distribution of y given x. So that's kind of a basic justification for how ingression can learn the distribution. Okay, any questions? Good. And so after this is not the end of the story, because now we obtained such a model that can allow us to draw samples from this distribution, and then what we can do with it, we can estimate all of the functionals of the distribution. So, and specifically by Monte Carlo, specifically for any fixed test point x, what we do is this is a procedure. We draw a sample of epsilon, let's say of size m, so from epsilon 1 to epsilon m, from standard Gaussian, and then we plug them into this fitted ingression model G tilde. So we get this G tilde of x comma epsilon I with I from 1 to m, And that's a sample of the estimated distribution of y given x. And if the generative model works well, if it approximates the true distribution well, then this is also a sample that is of a distribution that is very close to the target distribution. And then we define the estimators as using the empirical quantities of that sample. So let's say if you want to estimate the conditional mean, then you just take the empirical mean over epsilon. So you take the empirical mean of this sample as the conditional mean estimator. And it's the same for quantiles. Okay, so that's how you can make use of generative model to estimate any functionals of your distribution, and they are going to be automatically consistent. So in a sense, if you estimate quantile, they're going to be ordered. Yeah. And so we provide R and Python packages for our method, and it really works in a fairly standard way. So for example, the R package. So I just want to ask people in the audience to like how many people use R more often? Okay, good. Then we're going to demonstrate the R version. So it actually works in a very similar way to GLM. So we just like the package, and then you have your data matrix X and Y. You call this ingression function applied to your data matrix X and Y, and you have this object ingressor. And then you call this like built-in predict function, and with a specific type for mean prediction, quantile prediction, and sampling. So it's kind of all the neural network fitting is implemented in this ingression function. So you don't have to do anything. All the stochastic gradient descent is automatically implemented there. Okay, so it's very easy to use. Feel free to try it out. Okay, and here I just want to show you some examples to show that ingression actually works in real applications. So it's not just a toy method. So we've been this is actually where we started proposing this ingression method for this climate downscaling problem. So the problem setting is like this: we want to predict the climate, but it's a downscaling setting, meaning that we take the low resolution global climate data from a physical climate model as input. So the resolution there is very coarse, it's very low. And then we want to, given that, we want to predict the high resolution regional climate data. So we want to make the resolution finer. And that's a conditional distribution learning problem, because so here that's the high resolution climate map is our y, and the low resolution one is x. Then we try to learn the conditional distribution of the y given x in this case, and we apply ingression to that. And so we collect the pairwise paired data, and we fit our ingression model, and then this is how it works. So we take this specific observation of x, and then we draw 5 realizations of epsilon. And then we plug this x and the 5 epsilons into our ingression model, and here's the output. So these are, in a sense, the samples you draw from your ingression model from your estimated conditional distribution. And I will compare the samples with the true observation of the y, and we can see they share the similar overall pattern, which is good. And also there's also variation among different samples, for example. So this is temperature data. So around this region, for example, the second sample has a slightly lower temperature than this one. And we hope this would capture the uncertainty in the underlying distribution. So that's how this method works. And if you are more interested in this climate application, I think in a month I will give a talk at CSSS about this climate project itself. So feel free to go to that talk if you're interested. Right. So just to summarize the intro part, we introduced ingression as a general distributional learning method. So compared to traditional distributional regression methods such as quantile regression, ingression is more flexible. It doesn't have a quantile crossing issue, and it can make use of the expressive capacity of the neural networks to alleviate limitations of parametric assumptions. And it's also it's scalable to high dimensional X and Y. So for example, in the climate example, the dimension is about 100 by 100. So it's more than 10 to the power 10,000. And also compared to modern generative models, such as diffusion models and GAN, ingression is simpler. So we can have an R package for that, but you can't imagine having an R package for diffusion models, for example. And so it's computationally lighter because it's a one-step generation instead of doing like multiple steps in diffusion models. And it doesn't have a discriminator, or it doesn't solve a minimax problem as in GAN. So it's computationally lighter, and it also has fewer tuning parameters. We'll show an empirical result later to kind of validate this. And also compared to generative models, where the end goal is often data generation, like image generation or text generation, here we focus more on downstream estimation of the inference after we get an estimate of the distribution. Okay, so right, good. So now we just have a simple but flexible enough tool to estimate a distribution, and then we can look at how we can build methods upon this one to address the different types of generalization problems. Okay, any questions so far?
Yes. So in your case, neural network, you treat X and X as expected.
Yeah, exactly. So the neural network would just concatenate them, and we fit the longer vector into the neural network. Yeah, but in training, they're not symmetric. Yeah. Okay. So the first problem that we're going to talk about is the out of support covariance shifts or extrapolation. And this is based on a joint work with Nikolai Meinshausen. So we try to motivate the challenge of extrapolation in non-parametric regression using this air quality data example. So here we have measurements of two pollutants, and we take one as a predictor and the other one as a response. And then we split the training and test set at the first quartile of the predictor. And so it's a completely out of support tested scenario, so it's very challenging. And here we look at how these commonly used models work in this case. So linear regression, it's just extrapolating in a linear way, so it can't capture the nonlinear pattern. And random forest is doing well on training data, but once we go beyond the training data, it is always the training support. It's just always giving us a constant value by definition. And if we do neural network regressions without any further regularization, and here's how it works. So we plot the predictions from different neural networks trained with different random initializations and different architectures. And you can see the predictions, the out of support behavior is very uncontrollable and very arbitrary. And although this is just one data example, these phenomena are actually inherent to these models. However, ingression can make a difference. So we apply ingression with exactly the same neural network architecture as what we did in neural network regression. And this is how it works. So the reliability of ingression doesn't break down immediately at the boundary of the training support. So it can extrapolate reasonably well until a certain point when it starts to diverge. And so I hope kind of this looks a bit surprising at this point, and then let's see why that's the case. So the first element is the modeling choice. So one of the most common ways to model the relationship between X and Y is the additive noise model. So we call it post-additive noise model. So Y is written as a function G of X plus some noise. And here we would like to bring up a new model class, which we call the pre-additive noise model. So here the only difference is the position of the noise. And of course, these are just so far just two model assumptions, and we know all models are wrong. But the question here is, can one of them be useful in terms of extrapolation? And the intuition is that the pre-additive noise can actually intuitively reveal some information about the true function outside the support. And by that, what I mean is, for example, if you look at this observation X1, which is very close to the support boundary. And if the noise realization eta 1 in this case happens to help us jump outside the support, meaning that the value x1 plus eta 1 is a point outside the support, then if the data follows the pre-A&M, then the observation of y is going to be the true function evaluated at that point outside the support. So even though we don't get to observe those noise realizations, but we know if the data follows the post-A&M, then some of the observations of y are already the true function values for points outside the support. Okay, right. So it means kind of the data. There's some information hidden in the data. If the data comes from the pre-A&M, then there's already some information hidden in the data that can tell us something about the out of support behavior. And the next question is how to capture that information. And here, another intuition is that to capture that information, we have to fit the full conditional distribution of y given x. So if we just fit the conditional mean of y given x by standard regression approach, it's not going to work. And the intuition is that it's the noise that's revealing the information. So we kind of need to recover the noise. And to recover the noise, that corresponds actually to the distribution of y given x. And if you just look at the mean of conditional mean of y given x, that's not enough to recover the noise. So we're not going to be able to use that information, right? So those are the intuitions, and they suggest there are two ingredients for extrapolation: a distributional learning method and pre-additive model structure. And it turns out that ingression has both ingredients. So ingression is a distributional learning method, and the ingression model class is this fairly general model class. It contains the pre-additive noise model. And so a pre-additive noise model can be parameterized in this way, where the unknown pre-additive noise can be parameterized as a function of standard Gaussian. Okay? But if you do a standard regression, a standard post-additive noise model, it's not going to work. It's not going to contain this pre-additive noise model. Okay, so those are the intuitions, and now we try to formalize those intuitions a bit with some sample theory. So this is a setup. We consider the well-specified case where both the true model. So the true model is a pre-additive noise model. In a sense that the data comes from, so y is a function g star of x plus some noise epsilon inside. And then the model class is assumed to be a pre-additive noise model as well. So it's a well-specified case. And the function class G is a class of strictly monotone, let's say strictly increasing function class. So it's still fairly non-parametric. And also we assume for simplicity that the noise is symmetric with a bounded support. And actually it's more challenging to have a bounded support than assuming the noise is unbounded. And we assume the training support is like the half line. So we're only interested in extrapolation on the right side, but it's just an assumption for simplicity. And let's first look at how regression fails to extrapolate. So we look at the median regression, L1 regression, to minimize the absolute error of y and g of x. So we define this class f of L1 as the class of functions of all the solutions of median regression. So what this means is that all the functions inside this class is going to match the true conditional median for x within the support. And the true conditional median function here, because g star is monotone, is increasing, and eta is symmetric, so g star of x is actually the true conditional median function. And so it means all of the functions in this class is going to match the true function g star for x within the support, for x smaller than x max. But what this proposition is telling us is when x is greater than x max, then the worst case bias you obtain from a L1 regression is already approaching infinity. Intuitively, this is because we only know all functions, they all match within the support up to a point x max, and they are increasing. And so once they go beyond the support, one increasing function could be very flat and the other one could be very steep. So their difference could already approach infinity. Right? So this is a challenging scenario for extrapolation. And under exactly the same setting, here's how ingression works. So we can show the ingression solution G tilde of x is equal to the true function G star of x for all x smaller than or equal to x max plus eta max. So there's a slight difference. We can extrapolate beyond, we can recover the true function for x greater than x max, but only up to x max plus eta max. So it's kind of, in a sense, how far we can extrapolate depends on the noise level. And the more noise we have in the data, in the underlying data distribution, the farther we can extrapolate. Okay, right. So this theoretical result is consistent with our intuitions. It shows how ingression can actually extrapolate better than regression. And now let's look at some numerical example. So the training data is generated from a sigmoid function, and the support is about is around -4 to 4. And the test data comes from the same function, sigmoid function, but the support is from -10 to 10. Okay. And here's how we first do a neural network quantile regression for 3 different quantile levels. And we plot the 3 different quantile levels in 3 different colors, and each block corresponds to a different hidden dimension of the neural network and a different number of layers. And you can see, like, visually, the results are quite messy, and the result is quite sensitive to different choices of hyperparameters. And in general, it can't extrapolate well beyond the training support. And we have also a lot of quantile crossing issue. And here's how ingression works with, again, exactly the same neural network settings. And visually, the first impression is the results look much cleaner. And so apart from these 2 cases where the hidden dimension, the number of neurons per layer is too low, it's only 10, so it's not able to capture the nonlinear function. But apart from those 2 cases, ingression generally works pretty well. It's very robust to different neural network choices, which is good news for practitioners. So it doesn't require that much hyperparameter tuning. And also, in general, it can extrapolate reasonably well, also beyond the support. Right, and we don't have quantile crossing issue. Okay, so that's a synthetic setting. And we've also done a large-scale real data experiments where we collect a lot of real data, and we do pairwise prediction. We consider out-of-support extrapolation scenario. So here we plot the out-of-support loss of ingression on the x-axis and the regression on the y-axis, like for each data set, for each hyperparameter setting. And then we can see most of the points are above the 45-degree line, meaning that ingression tends to have a smaller out-of-support loss than regression. So it shows on a wide range of real data, ingression can extrapolate better than regression. Okay. Right, and because ingression is a generative model, it provides estimate for the full conditional distribution. So we can also get the quantiles out of it, and then we can construct prediction intervals. And this proposition shows that we can, ingression can also recover the conditional quantiles for x outside the support. And then based on that, we can construct prediction intervals with conditional coverage guarantee outside the support at the population level. So this is definitely different from, for example, conformal prediction, because once we go beyond the supports, the exchangeability is immediately broken. And here's some numerical results where ingression is the only method that can maintain a reasonable coverage rate for out-of-support loss, for out-of-support data, so the yellow data. Okay, so the takeaway for this first case is that we combine, so ingression with a combination of a certain model structure, which is pre-additive noise model here, can lead to better general extrapolation than standard regression. Any questions? That's a symptotic result, yeah. So that's also a difference, but it's a conditional guarantee, yeah. Okay, so the second scenario is a general distribution shifts. And we're going to study the robustness on the general distribution shift. So this is based on a joint work with Alexander Hansi, Michael Law, and Peter Buhlmann. So here we are going to consider the multi-environment setting where we have data collected from multiple data sources. So this is heterogeneous data. We have basically a mixture of distributions. And we have M environments, and for each environment, the data is assumed to be generated from a certain structural equation model. And the structure here we are assuming is, so it's quite flexible, it's quite general. We allow X, the covariate distribution, to be arbitrarily different for different environments. But the structural equation for the response needs to be the same, stays the same for all environments. So it means the kind of underlying causal mechanism is the same for any environments, but the covariate distribution can be different. And so we designed the approach in this way. So for each environment, given a proper scoring rule S and a distributional prediction model, like a generative model, P theta of Y given X, we define the ingression risk per environment in this way. So it's the expected negative score. And when S is the energy score, this is just the ingression risk. And the method, the population version of our method, invariant probabilistic prediction, is just an invariant version of ingression. So what we're doing here, we try to minimize this whole objective function. And the first term is the sum of all the risks across all the environments. So we hope the model to perform well for all environments. And then we penalize the pairwise difference between the risks for two different environments. So that's to say, we hope the model to have kind of similar risks across different environments. So that's what we are doing through this objective function. And lambda is the tuning parameter. When lambda is equal to 0, this goes back to naive ingression, where we just pull all the data together and do ingression. Okay, so we're going to skip all the technical details, but we're just going to look at one real data example. So it's a single cell data application where we have 10 genes, and we take one gene expression as the response that we should predict, and 9 genes as the predictors. So one application scenario is maybe missing data imputation. You want to impute the missing gene. And for training, we have 10 environments. And what's more interesting is we have 50 test environments that can be very different from 20 environments due to new interventions on unobserved genes. And so what we're interested in is how robust our prediction models are on these 50 test environments that we've never seen. Okay. And here are the results. So on the left, we show the results of our method IPP. So what we are plotting here on the y-axis, we plot the regularization coefficient. And on the y-axis, we plot the worst case test MSE. So it's a maximum test MSE, maximum MSE across the 50 test environments. So that's commonly used as an indicator for robustness. And so we can see the results. So we try our method IPP with 2 choices of scoring rules. So one is log score, it's just maximum likelihood, and a scaled version of the so-called CRPS. It's a univariate version of energy score. So you can think of it as an ingression. And we've also tried 2 model classes. So a neural network model class and a linear model class. And so here are the results of them. So we can see a decreasing trend for all of them as we increase the regularization coefficient. It means that the regularization is doing something good. So it's helping with the robustness of the model. Okay. And on the right, we show the results from the competitors with the same metric. So we compare to anchor regression, distributional anchor regression, and Drake, which was our previous work, and a machine learning benchmark, VREX, which also uses neural network. And so we can see the worst case MSE of all of those methods are larger than the ones from IPP. So it means IPP can obtain a more robust prediction model for those unsafe test environments. Okay, so that's an empirical result. And what we want to kind of take away from this single empirical result, what's shown just from this one, is that there's again an intuition. So the target here, we're looking at MSE, so it's about mean prediction. And we're looking at robust mean prediction on the distribution shifts, right? That's our goal. And all the methods on the right, they are actually targeting the robust mean prediction. So in a sense, they're directly trying to find a mean prediction model that's robust. But what IPP is doing is to find a distributional robust prediction model, because it's an invariant. It's trying to find an invariant ingression model that performs well, that performs equally well for all environments. So it's in a sense trying to find a distributionally invariant model. And what's happening here is, in the end, we're able to identify a more robust model in terms of mean prediction. And intuitively, what's happening here is, if you look for the invariant mean prediction model, then your training data might not be heterogeneous enough. There might be multiple models, mean prediction models that are invariant. But in terms, if you look at the full distribution, then there might be very few models that are invariant in terms of the full distribution. So that's why, by doing IPP, by trying to look for the most invariant distributional model, we actually in the end identify a more robust model in the end, even just in terms of the mean. So that's the second example where we show how by fitting the full distribution, you can actually identify more. Okay, right. So here in this part, I mostly just talk about intuitions and method and simple application. So for more details, if you are interested, please refer to the paper. Okay, and let's just briefly talk about the third part. So this is a causal inference project where we try to estimate the causal effect. And this is based on a joint work with Anastasia, James, and Nikolai. So here we have treatment X and the outcome Y, and we're trying to estimate the estimate is the dual interventional distribution of Y given dual X, or in the potential outcome framework is the full distribution of your potential outcome Y of little x, right? That's our estimate. And all these conventional estimates like ATE are actually functionals of our estimate. And we consider the case where we have unobserved confounders that's causing both x and y. So we can't directly do ingression of y on x because that's going to be biased. So here we consider the instrumental variable setting where we have additional variable z that is called an instrumental variable. So z is directly affecting x, but it's not directly affecting y, and it's uncorrelated from h. And we consider the non-parametric IV case where both the treatment model and the outcome model can be nonlinear. And the tricky thing is these two noise variables, eta x and eta y, they are correlated due to the hidden confounder. Okay, so we first study the identifiability of this of the estimate in this setting. So we show that under some assumptions which are kind of classical in non-parametric IV, the interventional distribution of y even dual x, which is our estimate, is uniquely identifiable from this observed data distribution of xy given z. So that's the identifiability result, and it directly suggests a method to first estimate the observed distribution, and then according to that identifiability, that's going to be sufficient to identify this estimate. Okay, and that's going to be our method. But before introducing the method, I'd like to also mention that sometimes estimating the full distribution is also necessary to identify that causal estimate. And that's interesting because then you have to estimate the distribution. So I'm going to illustrate this through this simple case of under-identified IV case. So in this case, we have one binary IV, so the instrument is binary, taking 0, 1, and we have two continuous treatments, X1 and X2. And for simplicity, we consider the linear outcome model, and then the estimates are just these two coefficients, beta 1 and beta 2. Okay, that's a setting. And we, so the fact is that the two-stage least squares standard IV regression would fail in this case, would fail to identify beta 1 and beta 2 because, so what this two-stage least squares is doing is, in a first step, we regress these two treatments on the IV. So we regress X1, X2 on the IV. And then we get the two fitted variables, X1, mean of X1 and X2 given Z. And these two are collinear because we only have one binary Z. So these two are collinear. And if they are collinear in the second step of these two-stage least squares, we regress Y on these two fitted variables. But they are collinear, so we're going to be in trouble. We are not able to identify the regression coefficients in the second step. So that's how standard two-stage least squares fail. But this is actually an identifiable case. So two-stage least square can't blame the non-identifiability because it is identifiable. So this theorem shows that under this assumption that we're going to explain in a second, these two coefficients are still uniquely determined from this observed distribution. So it means if you apply a distributional procedure, you estimate that whole thing, that whole distribution, then you are good. You are able to identify the coefficients. And this assumption here is very interesting. So it means that the conditional distribution of your treatments, given the IV taking two different values, are different in more than just the main shift. So that's what this assumption is trying to say. So it means, given the IV taking two different values, the distributions of the treatments are different in a more diverse way than just the main shift. And this theorem is saying if that's the case, then a distributional procedure would be able to make use of that more diverse information to identify. But a standard two-stage least squares, which is just doing regression by just looking at the mean, is not going to be able to make use of that information in a more diverse information in the distribution. So it's a shame that there is information in the data, but we can't use it because we didn't estimate the full distribution. Okay? Yeah, okay, so now let's introduce a method. So the method is trying to, again, estimate the observed distribution of xy given z. And to do that, we apply, again, a generative approach. So we first build a generative model, but in this case, we try to estimate the distribution of xy given z. So we need to build a joint generative model for both x and y. And so the tricky thing is that because these two noise variables are correlated, so we can't just parameterize them as a function of independent noise, but instead we parameterize them as two functions of an independent noise variable and a shared noise variable. And this shared noise variable is supposed to model the hidden confounding effect. So that's the joint generative model. And from this, what you can do is, given the value of the instruments, you can sample epsilon and you can plug in these etas, and then you can draw a sample of x and a sample of y. So it's very easy to follow this generative model to draw a sample of xy given z. And that's how this DIV, our method distributional instrumental variable would work. So DIV is nothing but just ingression applied to this joint distribution of xy given z. So I hope this objective function looks a bit familiar to you. So it's like the same as an ingression loss, but here the response variable is the joint pair of the treatment and outcome, and your predictor is now the IV. And so we have here the true observation of xy, and we have here in the second term the a sample you draw from your joint generative model, and we've just seen how we can do that. And then in the second term, we're penalizing the difference between two random draws, the independent draws from your generative model. Okay? So we define the minimizer of this objective function as a div solution. And what we can show for that solution is that if we denote the solution by the notation star, then what we can show is we take the outcome model here with the so H star Y is the noise reparametrization of the outcome, and then this whole thing is actually following this target interventional distribution of Y given to X when we fix X, but we draw epsilon from standard Gaussian. So this is good. This is exactly what we need because this is the distribution, the interventional distribution that we're interested in. And now what we can show is we have a model that allows us to draw samples from this distribution. So then our job is kind of done. If we are further interested in the interventional mean function, we can just fix X, we compute the mean over epsilon, and we can use the empirical mean as the estimator. And for ATE, for different values of treatment, you can get the interventional mean and you take the difference. So that's how, and you can do the same for interventional quantile and the quantile treatment effect. Right, and as for this method, I'm just gonna show one example, which is kind of an unidentified case. So forget about the specific settings of the data simulation. What holds here is the conditional expectation of Y of X of the treatments given IV is something like a alpha times Z. And the variance of X given Z still depends on Z. And so alpha controls the dependence of the conditional mean on Z. And so if alpha is approaching 0, then it means the means are kind of the same. So there's no information in the mean. And those methods which only exploits the mean is going to fail. But we have more diverse information in the conditional distribution, in the variance, in that distribution, right? And we've shown here the results, the MSE of the estimated interventional mean function for different values of alpha. So we can see when alpha is large, then all of the methods work like more or less quite well. But when alpha is approaching 0, DIV, this distributional method, is the only method that kind of maintain that performance, that can still give a reasonable estimate for the interventional mean. Okay, so that kind of validates our simple arguments in the underidentified case. So you have to estimate the distribution, right? The third takeaway is distributional causal learning can identify the causal effects in more cases than two-stage least squares. So to summarize the talk, again, we try to convey two messages. And the first message is that estimating the full distribution can lead to better generalization beyond the observed distribution. And we've demonstrated this through these three cases. The first one is ingression with a combination of a pre-additive noise model structure leading to better extrapolation than regression. And the second case, we show a multi-environment invariant version of ingression can lead to more robust mean predictions than methods that only target the mean. And in the third case, we talk about ingression with instrumental variable for a distributional causal effect estimation, but that also has more identification, can identify more than two-stage least squares. Okay, so that's the statistical message, but how we do that is really based on ingression, which is a simple but flexible generative AI tool. Okay, so with that, I'd like to thank you all for your attention.
We started a little late, so we can have some time for 5 or so minutes for questions. Before I start checking the Zoom, let's start with any questions from the audience here.
It's very nice talk. So we have two questions. The first one is like in a setting where you can do both classic regression and ingression.
Yeah.
And for example, you estimate the same quantity, how will the result?
You mean the first setting?
Maybe the first setting.
Yeah, we were kind of we were evaluating alpha. for the same quantity, right? For the conditional mean.
Yeah.
So we were comparing, for example, for the real data results, we were comparing the MSE for mean prediction.
Yeah, so that, I mean, that could be influenced by like distributional shift from, from like
Oh.
the training and testing data. I mean, just the ideal setting.
No shift.
Yeah,
Oh, I see. You mean no generalization.
yeah,
Right. So by the way, the distribution shifts are the same for both. Yeah. And so for the RID setting, well, that's interesting because it kind of it involves how a neural network behaves. And so you would imagine, like in a classical setting, regression, if you look at the conditional mean prediction in the RID setting, regression should perform better because it's more efficient, statistically more efficient. It directly targets the mean. But ingression is trying to estimate the full distribution, so statistically it should be less efficient if you just get the mean estimator afterwards. But what's actually happening in practice is not like that. So for this real data experiments, I've also done like in support cross-validation. But the validation loss, the ingression also has a lower validation loss than regression. And we didn't report it because we don't know why is that the case. So because I would suspect it has something to do with overfitting. So ingression somehow helps alleviate overfitting, but we haven't understood why that's the case. Yes, but so that's to say, even in a IID case without generalization concern, ingression also somehow empirically has some advantage over standard regression. Yeah, but that needs more investigation and understanding. Yeah.
that's cool. Second, maybe just very briefly, the ID scenario is very interesting. Yeah, it's like you wouldn't be able to identify if you use standard two-stage least square.
Yeah.
But actually, like there's additional thing you can do here. For example, Eric's chatting, and now we also have some follow-up work. So we can also leverage the heteroscedasticity of the exposure given the instrument, and that can give you additional equation. And then you'll have like, two equations, and then you can identify two parameters.
I see. So that's exactly also in this binary IV and two treatment. Oh, that's interesting.
Yeah.
But in a sense, is it fair to say you are also kind of exploiting more information than the mean?
Right. Yeah.
Yeah,
that means the heteroscedasticity, and that gives
in the more like some assumption like this, right?
Yeah.
Yeah, that's interesting. So what we are doing is kind of, I guess if you know like how much heterogeneity you have, you can do it in a more efficient way than going like to the full extent estimating the full distribution. But what we're doing here is just like estimating the full distribution, and then you are good. But statistically, if you want to do a statistically more efficient approach, there must be better ways to do that if you know more about the assumption. Yeah.
Cool.
Thanks.
Ollie has a question, but before that, is your speaker on?
Right.
And then if so.
I think so, yeah.
Try talking and see if we can hear you.
I mean, Kevin, I could wait till sort of folks in the room ask questions. I'm not in a rush.
Oh, he is talking. But I can't hear you somehow.
Do you hear me now or no?
Yes.
Okay. There's a bit of an echo, so I could, if this is not working, I could ask you the questions later. I don't have to ask them now.
I think you're good to go.
Okay, good. Thank you. So very interesting talk. Thank you. I might have missed this because I was listening on remotely, but you talked about sort of confidence intervals and prediction intervals, and I think you mentioned that those would be conditional. Is that correct? Do you hear me?
Can you hear me now?
I can hear you now, but do you hear me?
Yeah, I did hear you.
Okay, cool.
Yeah, that's interesting. So I did talk about prediction intervals, but not confidence intervals.
Yeah, prediction intervals. Yeah.
Prediction intervals, they are conditional. Yes, they have conditional coverage. Asymptotic.
Okay. Yeah. Okay, thank you. And then so in that conditioning, is there basically how does the architecture of the neural network, or in general the success of neural network, fall into that conditioning, or is that part of that conditioning or no?
Oh no, that's well, no, that's not part of the conditioning. The only conditioning is is basically it's a covariance. We fix covariance to some fixed value.
So
And
that's the part that I'm trying to figure out. That sort of maybe I'm missing this point, but wouldn't there be variability with what the neural network learns? Are we somehow accounting for that variability when we think about the prediction intervals?
we should be, yes. So that's why it's a asymptotic guarantee. So we don't have any, so does it make sense that it's a asymptotic guarantee that it doesn't, so it's kind of all the randomness in estimation of the neural networks would go away when a sample size goes to infinity.
I see. So the assumption is that sort of neural network is correct, or sort of at least is good enough that sort of
yes, it's a well-specified case.
Okay.
Yes.
Okay, thank you. That's the part I was missing.
Yeah, thanks for the question.
Thanks. Any last question from here, the live audience?
Actually, I have a question online if you can hear me.
I didn't see you, Jessica. Yes.
Yeah, good to see you. I cannot see your face, but very nice talk, Xinwei. I just have one question, very simple question on the high level. I wonder whether the 3 applications you presented can also be done with other generative AI, not your ingression, but the more complicated, more difficult to train ones, like the GAN. Can you still do those tasks as long as you can get this distribution of y given x?
Oh, yes, that's a very great question. So the answer is yes. So in principle, you can, because all of our guarantees only start from the fact that we estimate the full distribution. And you can do that by basically whatever methods, not just generative models, but also maybe density estimation and so on. But and also in the extrapolation paper, in the first paper, we've done in the appendix, also we've applied GAN to do that, and it works. But it's a pain to train it, but it works if you spend sufficient amount of time. But with ingression, we just don't have to spend that much time to tune the model and to keep like also the model convergence, because it's a minimization problem, so you can track convergence. And for GAN, there's no way to track convergence because it's a minimax optimization problem. And for diffusion model, the thing is, if we are interested in the, for example, the mean, then what we're doing is by sampling, right? We draw samples for each test point X. We might need to draw 1,000 samples to avoid the stochastic, the randomness there. And with diffusion models, that's going to be a trouble, because you basically, if you have 1,000 test points, and if for each test point you need to sample 1,000 samples of Y, then and for diffusion model, each sample requires like maybe 500 steps to draw a single sample, then that's going to be computationally a disaster. So that's why, in principle, all of those generative models should work, and even more distribution estimation methods. But like ingression, it's so far the one that's kind of working the best empirically. It has this computational simplicity, and also theoretically, it's also more tractable.
I see. Thank you very much. So your talk today is mostly about 3 applications of ingression, but you didn't specify, or you didn't talk too much about the detail of ingression. So if I want to check the details, should I go to your 2024 JRSSB paper?
Yes, that's correct.
Okay, thank you.
Although I would have to say we haven't fully understood all the details, all the theoretical details of ingression yet.
No.
So there are still a lot to be done to, like, in order to fully understand what like, for example, what I just said about overfitting, about the IIDs, the performance in an IID setting. We had no idea why we had some intuitions, but theoretically we haven't fully understood why it works even better than regression in an IID setting. So there are still a lot more to be done, but so if we have done anything, that's in the GRSB paper.
Okay, thank you.
Thank you.
Thank you.
Well, with that, thank you everyone for coming to our first wonderful seminar. If Xinwei is also going to be at the dinner tomorrow, or you,
Yes.
you can come introduce yourself to her to learn about her, but you can also tell her how great Seattle and the biostat stat synergy is. Xinwei told me she enjoys outdoor things, so you tell her about all the wonderful things you do in Seattle. But without further ado, let's thank her one last time and then see you guys. Thanks, guys online.